going to start. Dzień dobry, witam.
Dzień dobry.
Yeah, I don't speak any Polish. That's the only two words I learned today. Hello and welcome to my session about Let the Machines Learn, which will be an introduction to Azure ML. The most important slide for the whole conference is this one for all the sponsors. I know you paid something for the conference, but still without the sponsors, I guess it would not be possible to have this nice conference here in this nice venue. So visit all the sponsors, of course, yeah, and tell them how you appreciate what they're doing for the community here. So who is me? My name is Markus Ehrenmuller. As you might hear from my accent, I'm not Polish, but I'm Austrian. Got a thick German language dialect or accent in my English. I speak German and I speak English. I also speak Danish because my wife is from Denmark. So this Jensen, this part of my last name is an original Danish one. You find my contacts here. I'm working with the Microsoft Data Platform since version 2005. Already got a little bit hands-on for the upcoming 2017 version. I'm quite active in the community, so I'm the past chapter leader for the Austrian chapter. So like the SQL PLSSUG, there's also PASS Austria. We also do SQL Saturdays. There will be another one in January 18th, which is actually a Friday. If you want to know why it's a Friday and not a Saturday, just approach me after the session. I'm glad to explain why we are doing this. And I would be happy if I see some faces from this room at the conference in Vienna. There's also a book out there, 2 courses on Pluralsight, and I was awarded with the beginning of this year as an MVP, and I'm really proud of this. Maybe it does not change anything for you, but for me it really does matter, and I care about this, so I'm really proud of this. So what is this agenda about, or what is this talk about? What kind of people did I have in mind, what you are interested in for this session? So we will talk about why we are considering machine learning at all. So why would you think about doing machine learning? What is machine learning? So what are the patterns and how someone could explain what machine learning is doing? Then we will take a look what is Azure machine learning. It is a Microsoft conference. Of course, we will look at the Microsoft offers in the cloud, and then we will go into demo mode. So the first 3 things will take me roughly 20 minutes, and then we will shift to demo mode, and then we'll demo throughout the rest of this session. I hope you're good with that. So why machine learning? Who is using machine learning, and maybe have you ever been in contact with some machine learning algorithms? I guess so, because machine learning is widespread out there. For example, spam filters. Spam filters are, when they are intelligent ones, then they are based on machine learning. That means that every user marks things which are spam as spam, and things which are accidentally in the spam folder again back to the inbox. And with this data, machines can learn and improve to detect spam or not spam, to distinguish between not spam and correct emails. Or pattern recognition. So I think the neural network was invented, or they came up with, because the US Postal Office had troubles they wanted to automate the recognition of the handwriting of people, so they could automate the post sending. And that's why they came up with machine learning algorithms. Also medical outcome. So if you have some biopsy and if this is sent out to the hospital, there is a chance that they're using machine learning algorithms to detect if there is something bad in the biopsy or it's all right. Another thing would be fraud detection. So if you pay, for example, I pay lunch with my credit card here in Wrocław, and 10 minutes later someone pays with the same credit card for lunch in Tokyo. That is easy to detect, but with machine learning algorithms this can even be improved. So the machine can detect patterns of your usual using your credit card, and then they can detect outliers of usage of your credit card, and then fraud can be detected, for example. Very famous example for the recommendation engine is Amazon. If you move something into the bucket, then Amazon shows you things other people also bought. Maybe that's not true, because they don't want to show you what other people also bought, but they want to show you things where they think you could be interested in. Even no other person up to now bought both of the items, but Amazon or Amazon's algorithms tries to find out what they could upsell to you. So now you're becoming a customer because you're buying something, then they can try to upsell something. Predictive maintenance, so that we find out that something is wrong with the machine before it's actually wrong, so we can shift something, shift the oil, shift parts in the machine before any bad things happening. Customer churn is a good example for things how machine learning could help to detect something, but it's also a good example to show how hard it is to cope with that information. So if I show you a list of customers and tell you that 8 of those customers will churn in the next 4 weeks, that's a real good information, but it is not as long as you cannot cope with the situation, as long as you don't have any idea how to prevent those customers from churning. So machine learning will not solve all your problems. It will detect something, will help you in your business, but will not be the solution for all of your problems, definitely. Yeah, price is also an example. I think Amazon also tried it once several years ago. I can remember that they had a really bad media because they offered for the same item to different people different prices because they wanted to find out how people react to those prices. Will they buy at a higher price or not? But the media was not very good with that because the people were not very happy with that Amazon will not show you the best price but try out to find out how much you are willing to pay for an item. So machine learning is basically something like the Farmer's Almanac. I don't know, do you have something like that here in Poland? We do in Austria, so if there's sunshine on May 16th, then you can expect that the next 4 weeks there also will be sunshine, for example. There are some rules people came up with because they detected patterns over years, over centuries, and that's what the Farmer's Almanac is. And there's actually a real almanac.com out there, the old farmer almanacs found in 1792, which is basically a machine learning algorithm, but the old way. So they just collect a bunch of data over the years and try to find out patterns and apply this to making predictions about when something happens on a special day, then you should cope with the situation like this. So maybe you should plant your seeds or not because of the weather and so on. If you talk more technically and think about how programming, how developing of program codes work, is usually you take data. So that's an input data, a file, a web service, or something a user enters into a form. And then we have an algorithm, which is called a program. And this data and the program together is thrown at the computer, and the computer makes an output. So it shows a message or orders something or whatever. With machine learning, it's the other way around. We take data, the input data, and we also take the output data as the input for the computer, and the computer spits out the program. So machine learning is about learning from data, input data and output data. And in the case of machine learning, this is not called program, but we speak about data models. So we can take something, take data, learn from the data, and we get an algorithm, a model, a binary representation of the relation between the input and the output data. Or, to make it more like mathematics or something like that, do is they take x could be, for example, the age and the education of someone, and we can think about maybe there is a correlation between the age and the age and the education of somebody and his income. So maybe there's a correlation with that. So x would be, x1 would be the age, x2 would be the education, and y would be the outcome, the income of the person. But the thing is, we are not sure about how the relation is. So there's a black box. We don't know it for sure. And probably there's no chance to find out what the true correlation is indeed. But what we do with machine learning is that we think of maybe there is a function available, a mathematic function, which is very close to the true relation between x and y. And maybe for our case, it's good enough to use the function, even when we know it's not the perfect solution, but it's a solution which is available. So we never find out the true correlation, but we can find out a similar thing. And that's the function we're looking for. And we can rewrite that y is a function of x. So the income is a function of age and education. And as you could imagine, there's always an error involved, because even if you know two people of the same age, with the same education, probably they will have a different income. So there's always this error involved, because there's some random things we never can detect and we cannot try to minimize. So we just have to accept this irreducible error, which is just noise, and we can concentrate on the function itself. So what we're trying to optimize is only the function and not the random error, which always will happen. So machine learning, how can we begin with machine learning? The first thing is that we really need to know what we want to detect in our data. So tell me something new about the data will not work. So machine learning is not like you're digging into a big mountain and looking for gold. When you don't know how gold looks like, you never will be sure if you detected it. So you first have to define what you're looking for, how gold looks like, and then you can dig into the mountain and try to find it. That was also the problem with 10 years ago we spoke about data mining. That was really like doing mining, digging into a mountain, and everybody expected that somebody will find the solution to all the problems in the data, but this will not happen. So you first have to define what question you have and try to find the answers through the data. And maybe you detect during the whole process that's not possible, that with that data you cannot detect the solution. Then you have to reframe the question or try to collect more or better data. That's the next thing. We also need enough data. So when we just have data for 1 week, we cannot do predictions for the next whole year, of course. So we have to collect the data, and because the model has to learn from the data on the one hand, and the model also has to be evaluated on the data. So I show some data to the model, and it can learn from that, and then I take other part of the data which the model has never seen and try to do the predictions and find out if the prediction is a good one or a bad one. So that's also the reason why we need lots of data, so we can split the data into training and evaluation and score data. And we need enough computing power, because doing all those experiments, digging into the data, finding out is there correlation or not, changing the parameters and so on, takes a lot of effort and needs a lot of computing power. And that's the hypothesis for this talk is that Azure will help, or machine learning will help that Azure will be more widespread, because it's a perfect solution for that you need for your experiments for a short time of period. You need lots of computing power, and afterwards you don't need this computing power anymore. So it would be not so good idea to invest in lots of hardware if you just use it for a certain time of period, and that's where the cloud services can come in. So what is Azure machine learning? That's the offer from Microsoft in the cloud. As it is in the cloud, it's an on-demand computer resource, so I just can't use it, and if I don't need it anymore, I don't use it anymore, I don't have to pay for it anymore. And of course it offers all the data storage services we know from Azure, so the blob storage, the table, the document DB is now renamed to Cosmos DB, SQL, Spark, Data Lake, you just name it. And we can also use web services, and as we will see during the demo, we can also convert our machine learning experiment into a web service, which we can offer to our colleagues, which we can offer to third-party tools, so they can use the insights I gained from my experiments for their applications. And it's part, so the big thing is the Cortana analytics. I think Microsoft again copied just a good idea from other companies. So when you ask somebody at IBM, what's the cool thing, they came up with Watson, and every cool new service is now part of Watson, even if it's not really connected to each other. And now Microsoft copies this marketing thing. So every cool thing, every new thing is now part of the Cortana analytics thing. So also machine learning is part of the Cortana analytics suite. When we start machine learning, we have to first define the question. So we have to be clear about what question we have and how we can answer the question. That's the starting point. During the experiment, maybe we find out that the question is not solvable, then we have to reframe the thing, but that's the starting point. And then we have collect data. In the best case, I already have lots of data in my company which I can use. In the worst case, I have lots of data which I can't use because the data quality is not that good, or all the attributes I really need are not in the data. Then I have to restart the thing, collect the new data, wait a certain certain period of time. So I have enough data, then I can restart my experiment. I also have to prepare my data, because usually the data is not collected in the way we need it for our models. So maybe there's data missing, maybe there's data types which are wrong, maybe there is even data wrong, so we have to get rid of the bad quality in the data. That's a whole process on its own. I will not show much of this, but you can expect that this will be the biggest portion of your machine learning adventure, is collecting and preparing the data. Then we have to choose a model. Lucky enough with Azure Machine Learning, there are not so many models out there right now, so it's easy to start because it's not overwhelming. If you go into more detail and, for example, use R, like I will do a session tomorrow on R, there are 10,000 grant packages out there with I don't know how many algorithms out there. That makes it really hard job to first define which kind of family of algorithms you want to use, and then you have to define on which package you will do your approaches and base on your algorithms. Then we have to split the data, because one portion of the data is used to train the model and the other one is to evaluate the model. Then we evaluate, and if you succeeded, then very cool, because then we can predict, or we can predict who of the customers will churn. We can find some measures to prevent those from churning. But when we have changed something in the system, because now we are email targeting them or whatever, offering them special services so they will not churn, then we changed something in our system, and then we have to restart again with a new question. How can we find out even those with the new measures, with the new service we are offering, preventing some of the people from churning, but still some of them are churning. So then we have the chance to relearn our algorithm and collect data and so on and so forth. So that's a never-ending circle with machine learning. So Azure Machine Learning starts with the business understanding. Then I have to. So that's also very important, and that's the big challenge right now, I think, because most of the people who are into the business are not statisticians, so they're not into data scientists, they're not into data science, so they really have troubles in understanding what data science is about, what those algorithms are about, and all the data scientists and statisticians are not really into the business, so they have to learn the business. So either of the group of persons have to learn something of the others. But that's really crucial, because if you do not understand the business, you cannot come up with the right questions, and you cannot find anything in the data if this doesn't make any sense to you, because you're not into the business. Then we have to access the data. Of course, we clean it, we select in algorithms and machine learning algorithm. We split the data, we train the model, we test and score the model, then we evaluate the model, and then we can deploy it as a web service, as I already said, which we will see in a minute in the demo. So in machine learning, it looks like this. Anybody is familiar with integration services? SQL Server integration services, yeah, looks like familiar. So we have some data flowing through the experiment. So we start up there with accessing the data. That's exactly the demo I will build afterwards. So that's an adult census income binary thing. So we know that based on attributes of people, if their income will be above 50k or below 50k a year. So we can, for example, target them via special emailing, because we know that this good will only purchase by people who are earning more money than the average, for example. Then we can clean the data by cleaning the missing data, select columns in the data set, so we get rid of data which should not be part of the model. Then we choose a model. In this case, it's a 2-class boosted decision tree. Then we split the data, showing just a portion of the data to the model, and train the model with this portion of the data. So the data is split into the training part, and only the rest of the data is used to score the model, so we can find out if the model is really doing a good job in predicting data which it never has seen. And then we can evaluate the model. At the very end, we can deploy the whole thing as a web service. And that's what the demo will be about. What about my timing? Took me 20 minutes, yeah? Very good. So, that's the web page we are going to. That's studio.azureml.net. You can start with this link, and you can use it for free to build your first experiments. That's what I'm using here. So I'm not using any paid subscriptions. I'm using the free offer. Everything you can see here is also available for you. So we sign in with a Microsoft account. Just choose this one, and then I have to enter my password. Seems to work. And what we're going to see is the working environment for the Microsoft Azure Machine Learning Studio. So we get a list of bunch of things over there. So there are experiments, web services we have deployed, notebooks, data sets I have uploaded, trained models I have saved, and settings. What we are going to do is creating a new experiment. Already created some here, but we are starting with a new one. And the really cool thing is that Microsoft really wants you to learn this stuff. So if you create a new one, it offers you a lot of samples there. So there's, for all of the algorithms which is available in HTML, there's already an experiment there, which is explaining to you how the experiment is working. There's documentation out there. So there's no excuse to saying, I'm not sure how this works. There's really lots of stuff out there. You can go there instead for the party and learn all those experiments there. And with all of those, you can also you can open it in the studio or view in the gallery. Then it will expose the details, and there's written text which explains what the experiment is about, how it is working, why to choose this parameter or another parameter. But we're starting with a blank one because I want to show you how this is really working. And we're starting with a data set. So there are already I've uploaded some datasets, but in this case I use samples which are already out there. So they even prepared datasets which you can easily use. And I've chosen the adult census, like I've shown you in the first slide. And when I move it there, there's no parameters I can set because that's a fixed dataset. What we can do is we can always go to the circle in the lower end of the item, press the right key of the mouse, and visualize the data, so we can see what the data is about. And what we see here is that it's obviously 32,561 rows. Data scientists would call this samples, but people like me from the relational database, it's rows, and 15 columns. The data scientist people will call this attributes. So we see that there are 30,000 rows, 15 columns. One is, for example, age. We see through this histogram that we have more younger people than elder people. Work class might not be a good thing because everything is in the first thing. When I get those details here, we can see that almost everybody is a private and not so much of the others. So maybe we get just rid of this column for our experiment. That is another column. I don't know what this is about. Sounds Polish to me, but maybe does not sound Polish to you. And at the very end, there's this column we are interested in. It's the income. So it states this person with these attributes, 14 attributes, has an income lower than 50K. That's what we are up to. And that's what we want to predict for new data, based on what we can learn from this data. So the next thing will be to first select the columns. So I can always just browse through the long list, but usually it's better to use the search thing, select columns, and then I just connect those items so the data flows from the data set we just discussed to the next thing. So this has only one input and one output again, and here I can select the columns I want to include in my experiment. This is usually is to select all the columns and just exclude these ones we are not interested in. So for example, the work class was not very a good thing. Then the funny or I think the native country is also, we only have big portions of the data. big portions of the data is from the US, and there are other countries, and maybe that's not so very good to include it in the experiment. It could be that there are just 2 people from El Salvador, and both of the 2 people earn more than 50K. That could bias the data, and that could bias the whole experiment, so it's good to exclude this kind of column. The next thing is to clean up the data. Especially when data is missing. That depends on the algorithm you're using. So now I use the output from the select columns connected to the clean missing data, and we just stick with the default here. So depending on the algorithm, some of the algorithms get in troubles if there's data missing, and then we have several strategies how we can cope with that. We either substitute it, what I will do here, or we could with a fixed value, or we could substitute it with some of the averages, the mean, the median, or the mode. We could remove the whole column or remove the whole row, but then we will miss a lot of rows maybe in our data, or we could replace it by trying to predict what could be the content of this column depended on what we learned from the other rows in the data set. I just stick with the clean missing data to 0. So next thing is that we split the data. So we can we take the clean data set like here. Here it would be the whatever it did. Here's the cleaned data, and also this is one thing you can experiment with. So usually it's better to expose the bigger portion to train the model and the smaller portion to score the model, but it could depend on your data, depend on your model and you're using. So this could be one thing you could experiment with. So you build 2 experiments, one where you split it with 0.5 and the other one where you split it with 0.7 and try out what's the best approach for this kind of algorithm. The next thing is to come up with the model. So we use the two class boosted decision tree, and then we train this model. So we train the model. And training the model means that we take come on. Yeah, come on. So we take one portion of the data, the bigger portion of the data, and connect it to the trained model, and we take the model and connect it also to the trained model. So this portion of our experiment will train this model based on the bigger portion of the split data, and now it's complaining because I have to tell the trained model what I want to predict. So I want to predict the income. That's it. And then we score the model. Come on, so. Move it down there so we can move down here. Come on. I don't know what's happening here. So now we can move down here. And for the score model, we take the trained model, which is now capable of doing predictions for data it's never seen before, and expose it to the data it really has never seen before. And via this we can find out how good the prediction is doing. Either we do it on our own, or we use this evaluate model, which will show us some key measures we will discuss later on, as much as time will permit. Evaluating model has 2 inputs, so I can come up with 2 different models and evaluate them both, and they will be compared via the evaluate model. So that's basically is the quick version of this. We will return to each of those things again, but just now I want to run the experiment, which takes, I don't know, 30 seconds or something like that. And when we run this model, we can see, of course it's not fast. When I predict it's slow, it's fast, of course. So we've seen that there was a clock showing that this will be evaluated or running through in a minute, and the green check mark means that it's evaluated. We can then set up this experiment. So Usually, of course, you would now evaluate and go through and find out if this is really a good model. We just say it is a good model and take the shortcut and set up this experiment as a web service. So just with one click, we'll see the screen is moving around, so there will be an input, a web service input automatically created to the model and web service output. So I don't do anything here, this is just kind of magic. I then have to rerun the experiment here, and when I've done this, I can really deploy this as a web service. So now it's running through again. Don't ask me why we have to run it twice, but we have to, otherwise the button will complain. So the experiment is created, close, and now also the experiment is created, and we now can really deploy it as a web service. So the first thing was to create the experiment, and we could change it as well here. Afterwards it was created, and then we create a web service. And this web service can be exposed to anybody who is able to connect to Azure via the internet. As I'm not a developer, I can't use this API key, but I can use Excel. So anybody knows Excel? Huh? Who does not know Excel? Yeah, maybe that's easier. So we can open up the web service with Excel. It's now telling me that there's the possibility that I automatically add sample data. This is really cool because I can really do good demos and nice demos when there's already sample data available. So I'm not downloading an Excel file, that's the previous one. So I'm downloading a new one, which was just created right now, 1616. You see here the timestamp. So I enable editing. On the right part of the Excel sheet, it's opening an add-in, the Azure Machine Learning add-in. And yes, we want to use the experiment I just created a few seconds ago. Here I've got this button, use sample data. So automatically from my data I used to train the model, it's not just used to insert to Excel, so I have something to play around. Otherwise I had to come up with new data. It's easier to demonstrate here. That's the one thing. And the output should be in column Q, I think. So there's a space P. We see at Q, I want to have the output. And yes, it can overwrite data Q1. And I can also auto-predict, so every time I change something in the input, I automatically will predict my data, do predictions. So when we scroll over here, we don't see anything because, yes.
You need to click got it.
No, I had to, what I forgot is when this already was marked here, I have to mark it as an input. That was what I did wrong here. So now we have the input. In these cells, we get the output in Q1. Now we do. So as this web service is not really maintained, I just made it the quick and dirty way. The output of the web service is that it shows me all of the input rows again, which I would not do in a production environment. But it's added two other columns. The scored label, so where it says it's below 50K or above 50K, and the scored probability. So the probability, even every time when it's below 0.5, then it will say it's below 50K, and if the scored probability is above 0.5, it will state that the predicted income is above 50K. And now we can play around with that. So I know about the model that it's really into the capital gains. So this person is to be predicted that it says lower income lower than 50K. If the person had savings more than 7,000, it should show me a prediction of above 50K. So part of the model is obviously, or very important part of the model is the savings. So when the savings are higher, the probability raises that it will score higher than 50K. Otherwise, the model was perfect for the data I've shown it, because except this one there. So here the true income was below 50K, but the prediction was above 50K. So things happen, and we can try to improve this maybe by changing the scored probability, that we raise the scored probabilities so that we only accept probability higher than 0.6, and then we will treat the person that it will have an income above 50K. So that's cool, isn't it? how does this work? And let's go in detail for the experiment now, with the remaining time. So back to my experiment I just created, to the training experiment. As I said, always with the outset we have a context menu which shows us the possibility of downloading the data, so we can play offline with that, for example in R or something like that, or we can visualize the data. We already did this with the income. The income showed us how many rows are there, how many columns are there, and all the columns. And as we have seen, I can always click on a column and it will show me some descriptive statistics about this. So the mean is 38.5, the median is 37, so we are a little bit biased, so it's not perfectly normal distribution, normal or Gaussian distribution. The minimum is 17 years, the maximum is 90 years, with a standard deviation of 13 years. We have 73 unique values and no values are missing. Then we can show it this as a histogram, and this is very nice because now we see that there's some outliers out there with age of 75 or older, or even 70 and older, and the majority is up to 46, for example. We can this also change to a box plot. So when I click here at the box plot, then every attribute which is numeric is changed to a box plot, which is another kind of visualization to show how the data is distributed. So we see the median is at 38 something like that, and the 25th percentile and 25th percentile and 75th percentile is up to here, so that's the majority of the values. Then we have this interquartile range up to here, so those are the outliers, and then we have a true outlier, one person at the age of 90, so that's not the majority of the data, but that's an outlier out there. We can also dig deeper for not for the decision tree. So for the decision tree, we see that I just used standard parameters here, and an important number is this one, 100. That's the number of trees are constructed, because I used not just said that I want to build a tree, but I wanted a boosted decision tree. So that means that it made 100 trees, and we can see these trees. Not here for the untrained model. If I click here, I just see the different parameter I used to build the model, but we can see the actual trees at this as an output of the trained model. So what we get here is trees constructed, 100, that's just what I wanted from the model, and we can get details for all of the 100 trees, how they are built. So that's also a thing you should think about when you are using machine learning algorithms. Some of them are maybe not that good in doing accurate predictions, but they're easy to explain. And otherwise, on the other hand, you have, for example, neural networks, which can be in some approaches really, really good. So they make a really, really good prediction, but nobody can explain why it is. So when people ask you, why did the model predict when the savings are above 7,000, that the income will be greater than 50K, with the decision tree, we can answer the question, because we can visualize the decision tree and can really see how this actually worked out. So when we zoom in here, let's do this, then I have to click here. So we see for the first decision tree it came up that the most important thing is the material status. So if the person is married or not married. If the person is not married, it then looks at the capital gain, and if the capital gain is below 7,000, then if it's above 7,000, then it will say, yeah, let's add this as, yeah, when the capital gain below 70,000 is false, then we will state that the income will be below 50K. Or for those are married, not married, I think that's married, so 0 is not married, 1 is married. So when it's not below 0.5, the person is married, then it looks first at the education. And if the education, it's a numeric parameter, the education is below something, then it checks out the other things. And so it comes up with this prediction. It built up 100 of those trees and made the average of the outcome of all those trees as the outcome of the whole model. That's really cool, I guess. Scoring the model means that we can visualize how it did the job. And this looks like the Excel sheet we just have seen. So now we have not 13 columns, but 14 columns, because now we have these extra columns here. The income, up to the income was the input, and then we have the scored levels and the scored probability. And we see, depending on the scored probability, the scored level will be below or above. So if this is below 0.5, then we will state below 50K. If it's above 0.5, it will state above 50K. The real nice thing about the evaluation model is hidden here in the evaluate model. So here we get a parameter of how the model itself performed. So we trained the model with a portion of the data, and then we exposed it to previously unseen data, and tried to find out how it did correct predictions or wrong predictions. So one thing is this area under the curve. So the easy thing to remember is this area under the curve should be as big as possible. So a good model, or a perfect model, would have a straight line up there and a straight line down there. The closer the curve is to this diagonal, the worse the predictions or the model is. If the curve would be under the diagonal, then something happened wrong with asking the question. You just reverse the model then, so you get again a big space under the curve, around the curve. The more easier thing is here. So what we see here is the true positives. That's we can zoom in here. So what we see here is the true positives. So that's the people my model predicted that they will be above 50K, and they really were above 50K. That's the true positives. We also have the true negatives. That's when the model said in 6,868 cases, the model said this person has an income below 50K, and indeed it was below 50K. That's the good thing. The negative things, or the false things, are those where the model did the job wrong. So the false positives are those where the model predicted that this person will have an income above 50K, but indeed the person did not have an income above 50K. And the false negatives is when the model predicted that the income will be below 50K, but indeed it was not below 50K, indeed it was above 50K. And with that we can calculate the accuracy, the precision, the recall, and the F1 score. For all of these numbers, the shortcut is the closer they are to number 1, the better they are. But the thing is, how can we decide if this model is good or not? This depends on how your business case is. So if we watch the false negatives here, 70-63, and I change a little bit of this threshold, the more I lower the threshold, the more the false negatives will be lower. Can you see that? So that's easy to do. We can get rid of false negatives by lowering the threshold. But if you look closer to the false positives, the more I lower the threshold, the higher the false positives come. So there's always a trade-off. Either the model is good in avoiding false positives, then I will have a lot of false negatives, or the model is good in avoiding a lot of false negatives, then I will have a lot of false positives. And the thing is, which is better for my, or what is cheaper for my business. So if you think about security, if you're flying, you're going through the security, we want to get sure that everybody who has a forbidden item with him, a weapon or something like that, that will detect this. So when someone gets through and has a weapon, we don't want that the person can get through the security without discovering the weapon. So the false negatives should be really, really low. We will not allow people going with a weapon on the airplane. But this means that we have a lot of false positives. But at security, we can live with that. So you go through, you don't have a weapon, but the thing is beeping because you discovered something which is not there. They check you and everything is fine. So in this case, having a lot of false positives, but lowering the false negatives is not a problem at all. The other way around, if you think about spam filters, I really want urgent emails getting to my inbox and not to my spam filter, because I never take a look to the spam thing. So in this case, I don't want to have false positives. I don't want that the spam filter detects spam which is not spam. That would be a false positive. So in this case, I will optimize the model that I have a low rate of false positives. Maybe I have a higher rate of false negatives, so some of the emails which are indeed spam get into my inbox. I can live with that, as long as the majority is covered by the spam filter. We can also get a closer look on this, which I have here. So this model sometimes changes the values. I just check if I really get the right numbers. 1581, yeah. So I've got this here. I took this from a blog post from Microsoft, so you can play around with those true positives and false positives and find out how this accuracy, precision, recall and F1 score is actually working, because the formula is exposed here. What I try to do is make it easier, so I came up with an artificial experiment. Let's say we have 1,000 samples, and in this 1,000 samples there were 6 positive events, whatever this was, and 994 cases of negative events, whatever this means. My model predicted for those thousands, 992 were negative and 6 and 8 were positive. So 8 of those I predicted as positive, 5 from them were indeed positive, but 3 I predicted positive were indeed negative. For the 992, it's the other way around, I predicted 992 as negative, but only 991 are indeed negative, and 1 I predicted as negative, which was indeed positive. With these numbers, now we can play around and understand the accuracy. So the accuracy is the true positives plus the true negatives, so that's the total. No, it's not the total. It's the true positive plus the true negatives divided by the total. So that's telling me how accurate my algorithm is. In which cases I really made it. The negative thing with the accuracy is I can easily get a higher accuracy, for example, if I just predict that everything was negative. Because we have a really low positive event rate, but most of the events are indeed negative. So if I come up with an algorithm which just tells me everything is negative, it will have a high accuracy, which is not so good in many cases, I guess. So with this helps the precision. Precision is a measure which takes the true positives. Can you read this on the screen there? So the true positives divided by the true positives and the false positives. So that's those two numbers. So that's telling me from those 8, I detected 5 positives which were indeed positive, but at the whole I had 8 I detected as positives. So how many of those I detected as positive were indeed positive? So if I'm looking for being very accurate in finding the positive ones, then I'm going for the precision. The true positive rate or recall or sensitivity is telling me how accurate it is detecting the compared the true positives with the sum of the true positives and the false negatives. So of those I detect as positive, 6 were indeed positive. How many of them did I indeed detect? That's the sensitivity. So 6 people went through the security, and 5 I detected they had a weapon on it, but one person I missed with that. And as a combination, so if the true positive is really important for me, avoiding the false positive is important for me, I'm going for the precision. If avoiding the false negative is really important for me, I go for the false negative. And F1 score is just a combination of the both of them, so maybe that could be a good compromise, which we can see, I think, here in the, what's it here? Yeah, here I've got this. So if the false negatives cost more, false negatives are those where I do not detect the person going with the weapon through the security gate, which is might be very costly in here because there's life at danger. Then I will optimize for the recall. So the recall should be close to 1 and not very low. If the false positive costs more, so if I miss some of my emails because the email was moved to the spam folder by accident, then I will optimize to using the precision. So those will be optimize this measure. And if the false negative and false positives cost roughly the same, so I can't optimize for either one or the other, I going for the F1 score. I could use the accuracy if the class is really distributed even, which we do not have here. An even distribution would be that 500 would be positive, 500 would be negative. That would be an even distribution. In this case, I could go for accuracy. If it is not, or I don't care or I don't know, I stick with F1 as the thing I want to optimize. So that's the numbers I see here. I can try to optimize in my model. For the area under the curve, that's looking like this. So I've got explanation for this. So the different areas under the curve, the most favorite one is the ROC call, ROC plot, which is the plot we've just seen in Azure, like here. So I'm going to explain what's happening with this plot. Basically, there's also an Excel file you can download from Microsoft. I will upload the file together with my slides and tell you via Twitter. You can just include all the data from, for example, the Azure Machine Learning thing. Download it as a CSV file. And then we have the following table where I calculate for different thresholds. So the threshold is this thing where we can play around. I played around with different values for the threshold here. And if we put the threshold to 1, that means that if you're really sure, then we will call a thing positive. This will lead to something that we don't have any true positives, we don't have any false positives, because none of our prediction will be at level 1, but all of them will be negative, some of them will be false negative, some of them will be true negative. On the other side of this table, I have the value 0, so I don't care what it is, what the prediction is, how high the level of the prediction is. I always will say that's a positive one. Of course, this leads to some of them will be true positives, some of them will be false positives, but because the level is at 0, I don't have any negatives, because everything will be predicted as a positive thing. And then there's plenty of space in between, which we can see here. So the true positive rate, of course, increases with the threshold. The higher the threshold is, the higher the true positive rate is, because the lower the threshold is, the lower the threshold is, the higher the true positive rate is, because only when we have a very low threshold, then the probability that something will be attributed as positive is very low, and those which are attributed are, of course, true. It's the other way around with the false positive rate, false negative rate, false true negative rate, and the precision. We can then calculate this error on the curve, which is shown visually in the charts. So this is only combination of the true positive rate and the false positive rate, showing the point on the chart, like we see here in this table. So the true positive rate and the false positive rate combined, giving the area under the curve. For the false positive error rate, that's of course 0 when the threshold is 1, because none is, I don't have any false positives, because I don't have any positives. The false negative rate is 0 at the other end, because I don't have any false negatives, because I don't have any negatives. But what's interesting is the combination of that. So the error rate, where is the error rate very low? If I try to optimize both ways, so I want to have a low true positive rate and a low false positive rate and a low false negative rate, I can optimize for this error rate, and that would be that I put the threshold close to 0.55. That would be the outcome of this. Here we have an accuracy of 86. The precision, which is only looking for the false positives, is 100% here. The recall, which is only looking for the false positive rate, is down here, 100%. The F-score is in the middle, and now the costs come in place. So in all the cases where there's a different cost, for example, for the airport, there's a higher cost for false negatives than for false positives. If we ask people to come to an extra check, even if they don't have a weapon. That's totally fine for most of the people. But getting someone through with a weapon would be really costly. Then we could state it like here. So the false negative rate is 100 and the false positive rate is 10. So the false negative rate is 10 times more expensive than the false positive rate. And I can use this to calculate the false negative cost, the false positive cost, and come up with an optimal cost for the whole model. So if this is true that the false positive is cheaper than the false negative, I might go for a threshold of around 0.05 to optimize for the cost. With this said, I'm returning to my slides. Where is my slide? This is here. That's an overview about all available machine learning algorithms at Azure ML. You can't read this, I'm aware of that, but I will upload the slide, and this slide is also connected to a link, so in the PDF you just can click on it and you can download this from the original position on one of the Microsoft blogs about Azure machine learning. It's just showing you where you start, what's your problem, and depending on the problem you can choose some families of the algorithms. That's what the chart is explaining. So best practice for machine learning is more data is better. The more data you have, the more data you can use and expose to the actual model to train it, and the more data you can save from training to use it for evaluate your model. The more variable is worse, because the model will be more complex, the model will not be better and more accurate, but the model will be harder to explain. If you have lots of variables in there, it's hard to see which one of the variables is the most important one. If there's a bad solution, so we can come up with a model and the predictions is not very good, don't pursue on this model, try to find a different algorithm, try to maybe start from the beginning, try to use other kind of data to find a really good solution. And of course, like every time in life, think before you're acting, so really think through what is the expectation of the model, what is the expectation in the business, and what you can use the prediction to use for, because as I said, for the customer churn in most of the organizations, it's a good information to know that some customers will churn, that they will leave us, but as long as I don't know any countermeasures, as I don't have any ideas how I can cope with that, maybe the model is itself useless because it informs me about something I cannot take actions into. You can already start today, so Azure ML is out there. Studio.azureml.net is your friend to start your own experiments. Gallery.cortanaintelligence.com is the starting point to find out about everything else which Cortana is offering to you, which is indeed also machine learning algorithms, but they have a smarter API, so they use an API for face recognition, or you can use the API so it tells you what's on the picture and so on. So in the background there is machine learning, but the API is a different one. Yeah, don't forget that maybe it's I've got 2 sessions, so now there's a break between my 2 sessions, which is party. Don't party too hard, because I would really love to see you again at my session tomorrow, early at 9 o'clock in the morning, where I will explain or do an introduction into R, based from probably your knowledge about SQL and T-SQL. So we start with SQL and T-SQL and try to do things which we can already do in SQL and T-SQL to do this in R, so you have an easy start into this new language. Otherwise, I'm finished. Thanks again to the great sponsors. Chiqui, to say thank you for Chiqui. Okay, yeah. So if any questions, do it now, or just leave everybody and you just came out so everybody can have a nice party. And I say really thank you. Hope to see you tomorrow. Perfect.